So chapter 2 starts off talking about probability. Probability, generally speaking, is the study of randomness and uncertainty. Okay, and so what we're going to do is sort of define some things first, and then we'll be able to show some examples. So defining probability, the study of randomness and uncertainty. First, we have to talk about what it means to be a sample space. So having a sample space defines the set of all your possible outcomes. Okay, and we define that with little letter s. So if you see little letter s, then that means we are discussing our sample space. For example, what is the sample space for the days of the week? What are the options? All the possible outcomes for the days of the week. Someone take a shot at it. What are all the possible outcomes for the days of the week? I believe in you.
Monday through Sunday.
Thank you. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Those are all the options for the days of the week, okay? So then we can define something that we call our event. Maybe we only care about certain days of the week or whatever. We're looking for some sort of subset within our outcomes. So a subset of the outcomes, and we define that as big letter A. So we have a sample space, which is the set of all the outcomes, and then we have an event that we care about, which is a subset of our outcomes. So for example, what would be included in the event if we're choosing a weekend?
Saturday and Sunday.
Thank you very much. Okay, so that would be our event. Like we would say, we want a weekend, and so your subset of your sample space would be Saturday and Sunday. Not every day of the week, but only Saturday and Sunday is what you care about. Okay, so then we can define something. We'll define the word complement. Now, complement is going to be everything else, all the things you don't care about. Okay, so a complement we'll define as big A with an apostrophe. We call it A prime. Okay, so A prime is all the outcomes that are not included in our event A that we cared about. So if event A is the weekend, then what's the complement of the weekend?
The weekday.
Very good. And so what would those options be?
It's like Monday through Friday.
Very good. Questions so far? Okay, and now let's define what we call a union. Now, a union could be either A or B, so that we kind of put like a capital U between events A or B. So you would read that out loud as A or B, meaning either one is acceptable. Okay, at least one of these would be accepted. Now that's different than an intersection, which is stating we want the overlap of the two events, not anything that happens in A or B we're okay with, but we want only the thing that overlaps with A and B at the same time. Okay, so the intersection is A and B, not A or B, but A and B. So we want both things happening at the same time. And we write that as, I don't think we have, yeah, we don't have that. I'll have to write it by hand. It's okay, you take your U, but you turn it upside down. It kind of looks like an N, right? You're just switching that capital U, but putting it upside down. I think of it as an N, like N for intersection. I want the intersection of A and B versus the union of A and B. That's different. So I'll show you an example so that you can differentiate between these two. So let's say we are rolling a dice. And it's not one of those special dice, it's just a normal 6-sided dice. So what are the options when you roll a dice?
1 through 6. 1, 2, yeah.
Okay, so when you roll a dice, you could get 1, 2, 3, 4, 5, or 6. Let's define event A as we want to roll an even number. What's our subset there?
2, 4, 6.
Let's define what that would mean the complement of A would be. What would it be in words and what would be the options?
Any number not including 2, 4, 6.
Okay, so if it's not an even number, how would you define it?
It would be an odd number.
Mm-hmm. And what would those options be?
1, 3, 5.
Let's define event B as rolling a number divisible by 3. What would those options be?
3 and 6.
Question so far. Okay, so if I want A union B, that means I'm okay with anything that occurs in event A or event B. Any of those options would be acceptable, including any possibility from both events. So what would be my subset for A union B?
2, 3, 4, 6.
Okay, so you're going to include all possibilities. Now that's different than A intersection B. Okay, A intersection B means we only want the overlap. We want the overlap where both A and B are true. And what's the subset there?
3.
No.
Oh. Oh, it's this. Right. It's 6.
Yeah.
Sorry.
Yeah, that's all right. So we only are going to include only the overlap. Questions about that? What would be B prime?
One, two, four, five.
What would be, okay, so let's say B prime. It's 1, 2, 4, 5. What would be A union B prime?
One, five.
Questions? Okay, just note that let's say I asked you about the overlap and you couldn't find any overlap. If there are no possible outcomes, like for example, A and B have nothing in common, then we can call it a null event, which just means A and B are mutually exclusive. They don't affect each other. You could look at them as like disjoint. They don't overlap at all. Okay, and the symbol that we use to state that that there's no outcome is like a 0 with a slash through it, kind of. Okay, so visually speaking, this might help if we draw some pictures. So let's draw some Venn diagrams. Okay, so let's say I'm going to try and use different colors here. We have event A is blue and event B is red. If I wanted the union, okay, or again, it's written like this, A union B, then that means that this app updated recently. I don't know where all my options are, so hold on. Okay, so that means that I'm okay with both anything that happens in A, and I'm also okay with anything that happens in B. So any of those options are acceptable. I'm cool with all the things. Now, if I want to compare that to the intersection meaning instead of the big U, we're doing like a upside down U or an N. I look at it kind of like an N. I only want what is true for both things simultaneously. So I want only the overlap here. Okay, now if we want to represent the complement, so let's say we wanted to do A union B prime, then we are saying that we're okay with everything that's not the union. So we would say everything else. Or if we wanted to show events that were mutually exclusive, then we would show that there is no overlap at all between those two events, and so there's nothing to shade. So you would write A intersection B is null. Questions about that? Okay, so some notes here. That all the probabilities what do they add up to mathematically?
100?
Yeah, 1 or 100%. So you can use that knowledge calculation-wise. If you wanted the probability of a complement of an event, then you would just do 1 minus the probability of that event. Okay, and then also if you wanted to calculate the probability of A union B, You could take the individual probabilities of A and B and add them together, but there is that overlap, so you would need to subtract out the overlap so that you don't accidentally double count it. So going back to the dice example, if we wanted to calculate the probability of A union B in our dice example, and we wanted to use this formula, what is the probability of A? So just A specifically, how many options were there out of 6 for probability of A? Very good. And then if I did that separately for probability of B, how many options were probability of B?
2.
Okay, but there was an overlap.
1/6.
Yeah, the intersection of A and B, there was one option that overlapped, so we don't want to double count that, so we subtract that out. So you end up getting 4/6, which reduces to 2/3. So that would represent your probability of A union B. Where's the undo button? Okay, everything has changed. So as you notice, what we did, if we're calculating the probability of A, we're essentially just putting in the numerator the number of outcomes in A divided by the total possibilities, the total sample space. Okay, so if we were to just look at our notes and say, well, if we wanted the probability of A union B, we wrote down all those options. How many options were there?
4 out of 6.
Correct, which is why you get the same answer. When we naturally wrote down that subset of A union B, we naturally knew not to double count one of the options, right? Questions so far? Okay, let's define something which we call a permutation. So a permutation is an ordered, very important word, ordered subset. So this might be something like your ATM pin or the code that it takes to punch into your phone to sign in. You know, 1, 2, 3, 4 is not the same as 4, 3, 2, 1, right? Like if your friend picks up your phone and tries to sign in and enters in 4, 3, 2, 1, but your code is 1, 2, 3, 4, it's just going to say you're wrong. So the order does actually matter, even though technically you're using all the same 4 numbers, but they're in a different order. They count as 2 different options, right? Because they are 2 different codes. So when order matters, 1, 2, 3, 4 and 4, 3, 2, 1 count as 2 different options. So you can just write down Okay, so the equation for a permutation is npk, which equals n factorial over n minus k factorial. So n representing the total sample size, k representing your subset. What does that exclamation point stand for?
Factorial.
Define factorial.
It is the number and any number previous.
And what's the computation you're doing?
You're adding it. So it's like, oh no, wait. I have to find it.
So how would you define, for example, 5 factorial? What would you do?
5 times 4 times 3 times 2 times 1.
Correct, it's multiplication. 5
Oh,
times
sorry.
4 times 3. It's okay. 2 times 2 times 1. Okay. All right. Now, this differs greatly from what we call a combination. So a combination is something that we actually don't care about the order. So it's an unordered subset. Now, an example of this might be if I have a bunch of marbles in a bag and I'm pulling out marbles and I pull 3 marbles out, I get green, green, red. And then I do it again and I get green, red, green. Ultimately, I just pulled 2 greens and 1 red, right? Like it didn't really matter what order I pulled them out. When I grabbed 3, I got 2 greens and a red. I didn't really care about the order. So if I were to have a green, green, red, or someone else picked out green, red, green, it doesn't matter. They're equal to the same thing. Because of that, they're the same option. I got 2 greens and a red. It doesn't matter that they came in different orders. So they actually count as 1 possibility, not 2. Because of this, the equation for combination is different because we kind of have to divide out the overlap. We don't want to double count green, green, red, and green, red, green because they only count as 1 option. So you'll notice that in the denominator, there's more to divide out. We have k factorial times n minus k factorial here in the denominator. Now, the book, just FYI, might notate it like this. If you see like parentheses with 2 numbers inside of them stacked on top of each other, that's the same as NCK. That's just how the book does it. So those are the same, they mean the same thing, although they look different notation-wise. Okay, so just realize that this is how you can differentiate whether it's a combination or a permutation, is asking yourself if order matters. And if order doesn't matter, then you have to divide out the overlap. So just note that combinations will always be less. You'll have less answers, like less options, right, than permutations. Because order doesn't matter, so the repeat possibilities are divided out. Okay, so just make a note to yourself that you should always start by asking yourself, does order matter? And that is how you'll know which equation to use, because obviously you're going to get a different answer if you use the wrong equation. So let me show you an example. So let's do an example. Let's say that there are 7 runners in a race. Okay. The question is, how many different ways can they finish in first, second, and third place? So your step 1 in these problems is always asking yourself, does order matter? Yes or no?
Yes.
Correct. If I got 3rd place, I'd be a little less happy than if I got 1st place, probably, if I'm running a race, right? So 1st, 2nd, and 3rd do matter. So the answer is yes, which means...
We use the permutation formula.
Very good. Step 2, define your N and your K. So what is N, your total sample size, and what is K, your subset?
N is 7, K is 3.
Very good. Step 3, plug it into your equation. So you have 7p3. So what should I write?
Seven factorial or 7 minus 3 factorial?
Okay, so what I like to do is figure out what the denominator is first. What's 7 minus 3?
4.
Okay, so then I just write out the top factorial down to that number. So 7 times 6 times 5 times, and then 4 factorial, because I know now those can cross off. So what's my answer?
210.
So there's 210 different ways the 7 runners can finish in 1st, 2nd, and 3rd. And that's so many because 1st, 2nd, 3rd matter. If you just take the same 3 people and you jumble them in a different order, that's a new way of finishing the race. Take the same 3 people and jumble them again. That's a new way of finishing the race. And there's 7 runners. So now you have other runners you can involve. So there's 210 ways they could finish the race, 1st, 2nd, and 3rd. Questions about that? So let's do another example. Let's say that there are 7 runners, but this time we want to know how many ways can they appear in a photo of 3 for an advertisement flyer. So we're just trying to get people to show up to the race. So we just have like 3 people in a picture to create this ad. So step 1, does order matter?
No.
So what equation do we use?
N factorial over k factorial times n minus k factorial.
Yeah, so we're going to use combinations. Step 2, define your n and k. What's n, what's k?
Also 7 and 3.
Step 3, plug it into your equation. So you have 7c3. So what do I plug in?
Seven factorial over 7 minus 3 factorial, and then 3 factorial. Or, yeah, the other way too.
That works too. Okay, so again, I like to do the denominator first. 7 minus 3 factorial we already did last time. And then 3 factorial is 3 times 2 times 1. So then on the top, you can stop at 4 factorial because you know that those can cross off. But you can also reduce, like 3 times 2 is 6. So what do you get?
35.
So in this case, for a promotional flyer, there's only 35 different ways we can select 3 people to appear in the photos because we don't really care if we went with, you know, Grayson, Alex, and then Peng, or Peng, Grayson, then Alex, because all 3 of you are just in the photo, right? It doesn't really matter. So we're not going to count the order as 2 or 3 different possibilities. It's just one possibility to see the 3 of you in a picture. So there's only 35 ways, which of course is a big difference. Which is why it really matters to make sure you're picking the right formula to use, or else your answer is going to be way off. Questions about that? Okay, so like I said last time I saw you, is you should have your book ready during lecture because we refer to the book oftentimes when we're doing examples. So right now is a time to go grab your book if you didn't have it out already. If that's a virtual book, then open it up. If it's a physical book, you need to get up and go get it. We are about to do an example, so I want you to be able to refer to that example. I will not constantly flip back and forth between the book. I'm going to assume you are looking at the book on your own. So if you don't have the book, you need to go get it. So we today are going to be doing example 2.23, which should be on page 72. So right now, go grab your book if you don't have it out yet. So go grab your book, open up your book to page 72. And example 2.23 is in the middle of the page. So it says a university warehouse, here, hold on. I won't do this always, but for today, in case you don't have your book yet, I'll at least copy paste it into the chat. There you go. A university warehouse has received a shipment of 25 printers, of which 10 are laser printers and 15 are inkjet models. So when I see a problem like this with all these numbers and all these words, I want to organize what they're saying. I kind of want to pull out the information and simplify it. So I would start taking notes even before I've read the whole problem. I'm going to write down, I have 25 printers, and of those, 10 are laser and 15 are inkjet. I'm just going to write that down. And then it says, if 6 of these 25 are selected at random to be checked by a particular technician, what is the probability that exactly 3 of those selected are laser printers so that the other 3 are inkjet? So then I would just sort of write, okay, they want to know what's the probability of getting 3 laser and 3 inkjet when you pick 6 is basically the question, right? So again, the equation for probability is the number of outcomes divided by the total sample space. One thing that I want you to note is when you need 2 events to occur, you multiply. That's if you want like simultaneous. So we can elaborate. So if they say the word or, that's not what they said in this example, but if they say the word or, you're going to add the probabilities. So note that, you know, when you have a probability, it's like a fraction, right? So when you add fractions, your probability goes up. But if they say and, like they want both things to happen at the same time, then that's when you multiply. And because think of fractions, when you multiply fractions, your answer actually goes down, right? Multiply fractions gets you a smaller answer. So you can always ask yourself, well, is it harder for these 2 things to happen if I'm saying or and? So for example, if the probability of getting struck by lightning is very low and the probability of getting bit by a shark is very low, right? If I said, what's the probability of getting struck by lightning or bit by a shark, that means either option would be okay. Adding them together, you get a higher probability because a shark and struck by lightning, both very low, added together higher than that if I'm okay and I'm accepting either one as an option. That's the or situation, so you add them. Versus if I said, what's the probability of getting struck by lightning and bit by a shark, meaning I want them both to happen. Well, both of those options are very low. So the fact that I would want both of them to happen at the same time as well is even a lower possibility that that would happen. So you would multiply those 2 fractions and get an even smaller probability, right? So if you see the word and, you're going to multiply. If you see the word or, you're going to add. And in this case, they said and. So step 1, does order matter?
No.
So what equation are we going to use?
Computation.
It's going to be combination.
No combination. Sorry.
Mhm. Step 2, you want to define your n and your k. So we have separate n and k's in this problem. We have laser n and k. So for laser, what's our n and what's our k?
N is 10, K is 3.
Very good. And for inkjet, what's our n and what's our k?
15.
Very good. And then total, if you threw them just all in one pot, what is our n and what is our k?
$25 and 6.
Very good. Questions about that? So to plug it into the probability equation, in the numerator, we're going to be talking about what we want. So we want 10C3 for the laser, and we're going to multiply that by 15C3 for the inkjet, and we're going to divide it by the total possibilities, which is your 25C6. Now, at this point, you might think that's going to be a pain to write all that work out. So luckily, you have a good enough calculator that can do this by itself. So I would just write ask your calculator. And so how you do that, make sure you're using like your fraction button. Kind of looks like that. Use your fraction button. You can do it all in one step. You can also use the button that has NCR, and then of course use your parentheses. You should be able to do it all at once. So if you're using the TI-36X Pro, the NCR works like this. You put in the N, whatever your N is, for example, 10. You hit the NCR button. You see that factorial button? See how there's 3 options there? You have to toggle through between what you want. So if you keep pushing your factorial button, you use factorial, NCR, or NPR, and you just keep pushing it. So whichever one you want to use. In this case, we're using C. So you push it for NCR, and then you enter in your R3. So you would write 10 NCR 3, and that would give you the answer for that. You can do it all in one step. The fraction button is right above number 7, and then the parentheses are to the right of that. You can do it all in one step, and you should, so that you're not having any rounding errors occurring. So after you do all of that in one step, what do you get as the probability? Now, if you are using a graphing calculator right now, you're doing yourself a disservice because that calculator is not accepted on the FE exam, and you all should be planning on taking the FE exam. We can talk about that another day, which we will, but you need to start practicing with an accepted scientific calculator. The TI-36X Pro is a good one if you need to go buy one. There's a list on the syllabus for what are the acceptable calculators. What did you get?
I got 0.308.
Very good. And because this is not just a math class, this is statistics class, you've got to interpret that number, bring it into the context of the problem, and make a statement. So what does that 0.3083 mean?
probability of 3 of each printer getting chosen.
Yeah, so you would write a statement something like, there is a 30.83% chance of getting 3 laser and 3 inkjet when you pick 6 printers out of the batch. So always make your conclusion based on your numbers. Bring it into the context of the problem. So let's see if you can do one on your own. I will wait and see if you get it right. Tell me what the probability of 4 inkjet and 2 laser is. See if you can do it on your own.
%34.68% or 0.3468.
Correct. So the way you should have done it is 15C4, 10C2 over 25C6, and you would get 34.68%. Questions? I'm just going to check something. Give me a moment. Okay, so here are the questions from the problem. Okay. All right. Okay, so now let's talk about conditional probability. The equation for conditional probability is probability of A, given that B has occurred, is the probability that A and B occurred divided out by the probability of B. So what we're saying is, in words, conditional probability of A given B has occurred is equal to the probability of the intersection of A and B divided by just the probability of B occurring by itself. So, for example, if it is December, what's the probability that I might see a random guy walking down the street dressed like Santa, right? So the probability is probably higher that some random person's walking down the street dressed like Santa in December than in June, right? So given that it's December, now what's the probability I'm going to see someone dressed in a Santa suit? That's a different answer than given it's June, what's the probability of seeing someone dressed in a Santa suit, right? Or, for example, if someone just asked me, what's the probability that you're going to eat a corn dog today? Just today, I would say like 0%. I never eat corn dogs. Why would I eat a corn dog? I'm not 5 years old, right? But if someone was like, wait, you're at Disneyland. Now what's the probability you're going to eat a corn dog? It's like, well, I'm on vacation. I'm stuck in an amusement park. I can't leave and get healthy food. There's corn dogs every 5 minutes when I'm walking around. The probability of me eating a corn dog at Disneyland is higher than the probability of me just eating a corn dog by myself, like on a random day. Right? So conditional probability always talks about, given this specific situation, now what's the probability? Now, because of the given portion, the probability could be higher or the probability could be lower than just the generic probability of this event occurring, right? So to know whether or not to use this equation, you've got to look at the problem statement closely, see if there's like a comma in it. Like it'll say, if this has occurred, comma, now what's the probability that this will occur, right? So make some notes to yourself, like you should know to use this and not just like the normal probability equation when you see a comma in the problem statement. And not always, but it can be a hint, it can be helpful. So you know to apply this equation when a comma is introduced in the problem statement. So, for example, like they would say, like, if this thing has occurred, comma, now what's the probability that thing will occur? The probability of you getting stung by a jellyfish is different if I gave you the fact that you are going to be in the water on the beach for a week versus in the water on the beach for a day. Or versus you're never on the water, you're only walking on the sand. Those probabilities change. There's an overall probability of you ever getting stung by a jellyfish, but there's also different probabilities of if you're in the water a lot, a little, or none, right? Now, if you take this equation and you multiply the denominator P of B on both sides, you also get this equation. So you just multiply over on both sides, you get the probability of A intersection B is equal to the probability of A given B times the total probability of B. So both of those equations could be useful. So one way to visualize that is to use what we call a tree diagram. So I'll walk you through how to do a tree diagram, but you can just write So we are going to practice drawing a tree diagram by looking at example 2.29. So if you didn't get your book out the first time, you really should get it out this time. 2.29 on page 78. So go ahead and open up your book, turn to page 78. And example 2.29 starts at the very bottom of the page. It says, an electronics store sells 3 different brands of DVD players. Of its DVD player sales, 50% are brand 1, the least expensive, 30% are brand 2, and 20% are brand 3. Each manufacturer offers a 1-year warranty on parts and labor. It is known that 25% of brand 1's DVD players require warranty repair work, whereas the corresponding percentages for brands 2 and 3 are 20% and 10% respectively. So if you see a bunch of words and a bunch of percentages and you're like, oh, there's all these like if-then statements essentially, you should think to yourself, I got to draw a tree diagram so that I can organize all this information, okay? Because it's just like too complicated to hold it all in your head and understand all these if-then statements. So at this point, I would suggest you turn your page landscape if you can. I don't think this app will do it, which is really annoying. So I can't turn my page landscape, but you should turn yours if you can. Turn yours landscape. So doing example 2.29 on page 78, we are going to try and take all those words that I copy pasted into the chat and organize it via a diagram. So for example, we have 3 different brands we can buy. So you could say, well, I could go this direction, brand 1, I could go here, brand 2, or I could go here, brand 3. So I could say, I don't know what that was. I didn't mean to draw that. Okay. The probability of me picking brand 1 is what?
One and 3.
No.
Oh, you mean like the percentage that they're giving us?
Yeah.
Oh. 50.
Yes, very good. The probability of me picking brand 2 is what?
30%.
Mm-hmm. Very good. And the probability of me picking brand 3 is what?
20%.
Okay. Now, so this is brand 1, brand 2, brand 3. Okay, so then you've got, if you chose brand 1, all these things that could occur. You could maybe have to repair or maybe not have to repair your DVD, right? So we've got the repair option and we have a no repair option. If I chose brand A, brand 1, what was the probability of me having to repair it?
25%.
So I would label this as the probability of me having to repair it, given that I have chosen brand 1, is 25%. Now, if that's 25%, what's the other probability?
75.
The no repair. Very good. That's the complement. The probability of me not having to repair it, given I chose brand 1, is 75%. How about brand 2? We've got a potential repair or no repair. What is the repair possibility?
20%. 90%.
So I would write that as the probability of repair given I chose brand 2 is 20%, and the complement of that, the probability of needing no repair given I chose brand 2 is how much?
80%.
Okay, and then I have got brand 3 options. I have a repair option and a no repair option. The probability that I need repair given I bought brand 3 is what?
10%.
And the complement of that, the probability of not needing repair given I bought brand 3 is what?
90%.
Questions about how we got all those numbers? Okay, so looking at this first option, if I truly want to know what the probability is of needing a repair intersecting with having bought brand 1, I would calculate that by the conditional probability and multiply it by the overall probability of having bought brand 1 in the first place. Now that looks really complicated because I wrote it out that way, but truly all I'm telling you to do is to multiply. So you're just going to take this number and multiply by that number to get this number. So multiply those two branches and what do you get?
.125.
Okay, and to get the answer for this branch, do the same thing, just multiply the two. Now you could write it out like what I want is, you know, the probability of B prime intersection A1 is the conditional probability times the overall probability. What would you get?
.375.
Now the other option is to look at it as essentially the complement. So you could have done, well, what's the total probability of brand 1 and just subtract out the previous answer that we got, and you'll notice that you get the same answer. So let's do the same thing for this one. All you are doing is multiplying the branches. Technically, the equation here what do you get?
0.06.
Doing the same for this branch, you are just multiplying them. You could look at it like this equation. What do you get?
0.24.
Or you could have looked at it simply as the complement. So you could have said, well, take the total probability of A2, subtract out my previous answer, and you would have gotten the same answer. Here, you're going to do the same thing. What do you get?
0.02.
Finally, the probability of not needing repair intersecting with having bought brand 3 is the probability of the conditional times the total. What do you get?
0.18.
Or you could have looked at it as the complement of your previous answer. So the total A3 minus the answer we got before for the intersection. And you would have gotten the same number. So what you want to do then to double check all your work is to add it all up and make sure it adds up to 1. So double check that it all adds up to 1. And it does. But take some notes here. You are going to use the complement rule to fill out the missing probabilities. You don't have to, but it's helpful because if you calculate one, then you can just calculate the other by using the complement rule, or you can at least use the complement rule to double check your work to make sure it all adds up. You always want to make sure that you confirm that all the probabilities in your tree add up to 1. Okay, that will also help you make sure you're checking your work. And like I said, sometimes it's even worth points. And then here's my other thing, which I'm saying it now, so just realize I said it. Always fill out the entire tree. So I recommend always filling out the entire tree before you even look at what the questions are. We haven't even finished this example. We didn't even look at what they're asking us. We just drew the tree first. So always draw the tree first based on the information before you even answer the questions, because it's so much easier to answer the questions after you've drawn the tree. Now, some students might say, well, I don't need the tree. I can do without the tree. Well, then you're going to do without half the points on your homework quizzes and exams. Okay, just heads up. Do the whole tree if you want full credit. Always fill out the entire tree if you want full credit, and then answer the questions, even if you feel like you don't need it. Okay? Get it? Got it good? Okay, so here are the questions from the problem. Question number 1, it says, what's the probability that a randomly selected purchaser has bought a brand 1 DVD that will need repair while under warranty? Use the tree. What's the answer?
$25%.
What did you say? 25%? Where did you get that?
From the tree, at the very top.
Okay, so I'm looking at this number. We need this number because that's the combination of those two things happening. So individually, it's the 25% and the 50%, but for both of those two things to intersect, that's that 0.125. Make sense?
So 12.50 in this case?
Yeah, 12.5%, or you can just write 0.125, it doesn't matter. So number 1, you can just read it straight from the tree, which is 0.125. Turning to the next page in your book, number 2 asks you, what's the probability that a randomly selected purchaser has a DVD player that will need repair while under warranty? So that includes any brand, right? They just want to know needing a repair altogether. So they want to know the probability of needing a repair altogether. Well, there are 3 options. You could have chosen brand 1 and needed a repair. You could have chosen brand 2 and needed a repair. And you also could have chosen brand 3 and needed a repair. And either all 3 of those add up to the total probability of needing a repair in general. So what would that probability be?
20.5%.
Oh, yes, 0.205. Yep. Or 20.5%. Question 3. If a customer returns to the store with a DVD player that needs warranty repair work, so given that they're coming back needing a repair, given that they needed a repair, what's the probability, given that they needed a repair, that it's a brand 1 DVD player? What's the probability, given that you know you needed a repair, what's the chances that it's brand 1? So what we're saying is we want to know the probability that it's brand 1, given that we know you need a repair. Looking back at your notes, from conditional probability, the way you calculate this is just looking at the intersection of brand 1 and needing a repair. That's a portion of the whole, the entire probability of needing a repair out of brand 1, 2, and 3. So what number do I put on top?
Is it 0.125?
Yep, 0.125. What number do I put on bottom?
On the bottom. Should it be 0.25?
0.205. That's the probability of B, which is what we calculated in problem 2. So what we're saying is the probability of having bought brand 1, knowing that I walked into the store needing a repair, is just a portion of the whole. It's that portion of the intersection of brand 1 and needing a repair out of the total probability of needing a repair. It's just a proportion. So what do you get?
So you have to do that 2 more times, right? For 2 and 3?
For 2 and 3, yeah.
Mm-hmm.
0.609.
0.61, let's say. So then, yes, it asks for brand 2. So what's the probability that knowing you walked in the store needing a repair, that it actually was brand 2? So that is the intersection of brand 2 and needing a repair divided by the total of all the possibilities of needing a repair. What number goes on top?
.06.
0.060. What number goes on bottom?
0.205.
0.205.
0.205. What do you get?
.29.
0.29. And lastly, the probability, knowing that you walked in needing a repair, what's the probability that you happen to have brand 3 in your hands? That is the intersection of brand 3 and needing a repair divided by all the possibilities of needing a repair. What number goes on top?
0.10.
A3 given B.
Is it 0.02?
0.020, yeah. And total B?
In 1.
0.205.
Okay, so this is the proportion of the whole, the proportion of brand 3 people out of all the people that needed repairs is what proportion?
I got 0.097, so 0.1.
Okay, so 0.1. And add all those up for me.
One.
You should get 1. Yeah, you should get 1. So because of that, this one, you could have used the complement rule. You could have said, well, it's everything else. The probability of A3 given B must be the total 100% minus all those other two added together. The probability of A1 given B and the probability of A2 given B, because they all add up to 1. So you could have done that. Questions about that? There's plenty more examples in the book, so if you need more practice, go to the book, read the book, do more examples. And of course, you'll have a homework problem, so you can practice more with that as well. The last thing that I want to talk about in chapter 2 is independent events. Independent events mean that if one of them happens, it doesn't have any effect or bearing on whether the other thing's going to happen or not. So the occurrence of one event has no bearing on the chance the other will occur. So in that case, if they're completely independent, so before the numbers were totally dependent, because if I had brand 1, 2, or 3 and I walked into the store, there was definitely a different possibility, because maybe brand 1 was the better brand 2 is like the mediocre brand, and brand 3 is the worst brand or whatever. So there's higher and lower chances of me needing a repair. So those are dependent on each other. Independent events are things that don't affect each other at all. So it's like, did it rain today and do I have a sister? Like those two things, it doesn't matter. Like if it rained or not, having a sister doesn't affect the rain, and the rain doesn't affect having a sister. Okay, so these are things that don't affect each other at all, which means if I'm asking for the conditional probability of something happening given that something else happened, like what's the probability it'll rain today given that Deanna has a sister, it's still just the probability that it'll rain. It doesn't matter if I have a sister or not. So the probability that it'll rain, given that I have a sister, is just simply the probability it'll rain. It doesn't matter. They don't affect each other. So in independent events, the probability of A, given that B is true or B has already occurred, is just simply the probability of A, because it's not affected by it. Because B happening or me having a sister does not affect A, whether it's going to rain or not. So we're going to use this equation to check if things are independent or not. If those two sides of the equation are equal, then that must mean that these events are independent and they don't affect each other. If these two sides are not equal, then that means that one thing does affect the other. So use this equation to check independence. If and only if two events are independent, so once independent, so if you know that they're independent, then the probability of those two things occurring, so the probability that it rains and I have a sister, is simply just the probability that it's going to rain today and the probability that I have a sister. So you would just multiply those two independent event probabilities.
What does the IFF mean? Or the
If and only if.
Oh, okay.
Okay, so let's do an example where we check for independence. So let's say we have event A and then not event A. And we also have event B and we have not event B. There's 2 of these, 1 of these, 6 of these, 9 of these. So for the total, what's the total of the first column? B, column B.
3.
What's the total of column B?
It's 3.
Yeah, was that what you said? 3, yes. What's the total column of not B or B prime?
15.
What's the total of row A?
8.
What's the total of not A or A
2.
prime?
10.
Well, what's the total?
18.
Perfect. So you want to check that row and that column, they add up, and that's how you know you filled it out right. So that's step 1. And then let's figure out, we're going to look at that, that independent event equation and see if it's true. So what is the probability of A happening given that B has happened? So looking at that B column, how many of the B columns are A?
One.
So looking at the B column, how many of the B column are A?
Two.
2. So the probability of getting A, given that you're already in column B, is 2 out of what's the total potential? 3. 3.
3.
So this is the total B, and this is the A within the B column.
Wait, why is it 2? I thought it was just 1.
2 out of 3.
Like, the data in row A intersects the data in row B, and then we're looking at how many rows A
Yeah, so since it says, so remember, this slash means given. So given that we're in the B column, now what's the probability of getting A?
Oh, okay. Suppose A equal to like 4, it'd be like 4 over A prime plus A. Right.
You're just looking, the given is, whoops. The given, this given portion, you look at that column, and then you look at this row, and so that's the numerator and that's the denominator.
Can you scroll up a little bit? Just a tiny bit.
This way?
Yeah. Thank you.
Okay. Probability of A happening, given that B has happened. You're looking at row B, sorry, column B, and the only two options are A happening or A not happening. So A happening over the total. What is just simply the probability of A overall?
Is that 2?
So overall,
Overall.
there are 8 out of
18.
18. Okay, what do you get for 2/3? What does that come out as a decimal?
Or 6.
How about 8/18?
0.44.
Okay, if these two events were independent, remember A given B should just be equal to A because B should not affect it at all. But they're not equal. So if they were equal, you could say they don't affect each other at all. If they're not equal, then one happening must actually affect the other one happening. So since the probability of A, given that B has occurred, is not just simply equal to the probability of A overall, then the events are not independent. Which means B having happened already actually does affect A.
Can you scroll down just a little bit?
Okay, now down this way?
No, the other way.
Up that way, okay. There you go. Questions about that?
How would you read that statement since how would you read the first statement?
Oh, out loud?
Yeah.
Since the probability of A given B is not equal to the probability of A, the events are not independent.
Oh, okay. I see.
Can you just repeat yourself again one more time? How did you get 8 over 18? I know I got the first part, but the PA.
Okay, so the probability of A altogether is the total A's over the total.
Oh, okay.
The other one, the probability of A given B means we have to only look at the B column. And now what's the probability of A in the B column?
So, for example, if there instead of number 2, there was like a number 5, it will be 5/3.
Well,
Correct.
it'd be 5/6 because that's a new total, right? Right?
Oh,
If this is a 5, then now this total is 6, so it'd be 5/6.
Okay, I see what you're saying now. Okay, I see. Thanks.
Mm-hmm.